Well, hello. Welcome to Fractions. This is Doug. I'm ready to get started, but I know that students might still be trickling in, so I'll do my usual thing where I don't really talk about the math yet. But as you can see, I'm going right back to basics this week, not for the whole lesson. I'm just going to start off with a little bit of this pizza stuff, except I'm not using pizzas. So you notice there are no circles here. Although we all know you can make a pizza in any shape you want, really. You can have a rhombus-shaped pizza, but I'm going to stop talking about pizza. Okay, so what's going on? The weather is too hot. So that's not really going to have any impact on anything. It's still September, so the weather doesn't matter so much now. My beautiful assistant Mocha is upstairs. See my finger there. Because we gave her a sample of dog food that arrived in the mail yesterday, and it disagreed with her. So she was a little sick. It's very temporary, and it's not a big problem, but I don't want any of that happening while I'm trying to teach math. This shirt is West Ham. I'm sure I have worn it before. I have several West Ham jerseys. West Ham are from the East End of London, go figure. They are a soccer team. They are a pretty cool team. I like the shirt, but it's all covered in chalk dust right now because I have been teaching for hours today, actually. And I was wearing this shirt. So it would make a good chalkboard. Maybe I should try doing the problems right on it one day. Okay, I will keep an eye on the chat. It's possible that I'll see a suggestion from a student for a question that I want to use, but I also like to see it if the students are typing in answers and I look at the answers and it makes me feel that the students are following along with the lesson. I like that. I like to interact with the students. And I think it's important for the students, as well as what I always say about how you should have a sip of water and stretch sometimes, being involved in the lesson instead of just watching someone. So the more interactive a lesson is, the better. Okay, that's a good way to start. I think I am able to get into the math now. And just when you see me lean forward, it's just because I'm checking the chat in case if anything is getting in. To start with, all I wanted to do was to remind us that we can see a fraction when we have a shape that's divided into pieces, but the pieces have to all be equal in size to each other. Otherwise, it wouldn't be a really good shape to review fractions with. So with this rhombus, for instance, a rhombus is easy to divide into 4 equal pieces if we just draw in the diagonals, and it turns into a geometry lesson really quickly if we don't watch out. But I'm going to stop there with the whole geometry thing because these 4 pieces of the rhombus are equal in size and shape, although they're pointing in different directions, and I can do a fraction with this, and I want the student to identify the fraction. So I'm not going to say the answer right away. We have 4 pieces of this shape, and I am shading in 3 of them. So you tell me what the fraction is, and I won't give the answer too soon. We know a fraction will have a fraction bar, so there's the beginning of my answer. Taking a little bit of a look at the chat to see if any of the feedback is coming in. Okay, so when we divide the rhombus into 4 equal pieces, that means, yes, that the denominator is going to be a 4. And then how do we do this? What we have as our numerator is what we have out of the 4. So shaded is representing what we have. We have 3 shaded pieces out of 4. We have the fraction 3/4. It is really that easy, and it is that fun. Now a square is also easy to divide into 4 equal pieces, but I don't want it to be 4 equal pieces. So I'm going to start by dividing it into, 4 equal pieces. Doing my best. I don't have a ruler here. But then I can divide each of them up into smaller bits. So I think I'm going to try to do something really fun here. I'm going to draw diagonals in the 4 little squares that I made. And it makes actually quite a pretty design. But now I have 8 little triangles. Let's see, how many of them will I shade? I think I'm going to shade 3 of them. And of course, sometimes you always shade one section, and sometimes you sprinkle it around. This time I sprinkled it around. What fraction does that make? I'm taking my time to get around to saying it. I'll put the fraction bar. How many pieces were there? 8. Are they equal in size? Yes, they have to be. Otherwise, it's not a good shape to practice fractions with. So 8 is my denominator. And of course, the students are getting it, right? How many are shaded? How many do I have? 3. So if this were to be a pizza, it would be kind of weird the way people took slices away, but they left those 3 slices. That's how many slices we have. How many slices did we start with? 8. It works. Here's a rectangle. Rectangles are really good for this because you can always divide a rectangle into not just easy amounts like 4 and 8. You can divide a rectangle easily into any amount of shapes you want simply by cutting it into little strips. So I'm going to prove that by cutting this into, and I guess I'm giving away something. I'm cutting it, well, I'll just let you count actually. So what I'm doing though is you can see my strategy. I'm not going right to the midway point. I'm going a little bit above that. And then I'm doing this. And then I'm doing this. And I have a number, I didn't say what number, I have a number of equal shapes, equal pieces of this weird rectangular pizza with long strips for pieces. Okay, so what fraction? Well, I can't ask you to tell me what the fraction is unless I shade some in. But wait, what if I don't shade any in? So this represents a pizza that was cut into how many? Yes, I'm looking to see if students know the answer, and I knew that students would know the answer. I knew I'd see that. How many? 7. 7 is my denominator, but I didn't shade any. Is this a trick question? Well, kind of. So what this means is it was 7 pieces of pizza, if you will, but all 7 of them have been taken because Doug was really hungry. There are none left. 0. There are 0 shaded pieces. I guess I can say that I can do this. Might be a little bit confusing, but it doesn't hurt to do it once. Okay, 0 over 7 is my fraction, which means I have 0 pizza left. I have no pizza left. I have no pieces. I have no pieces of this shape, which is not a pizza. Okay, I'll just admit it. For me, fractions are always pizza. I don't necessarily say it out loud, but in my mind, I'm thinking of pizza. Here's another rectangle. This one I'm going to divide into 8 pieces, kind of like I did here. But now I'm not really trying to do mystery fraction. What I'm trying to do is to talk about why I think rectangles are so good. Now, this is a very good reason. The fact that you can divide it easily into 7, a weird number like 7 equal slices, 9, 11, 23. Any rectangle, if you make the rectangle big enough so that you can draw enough lines, can be divided into any number of equal pieces, which means they're really flexible for representing any fraction you want. That's the strength of the rectangle. Not always so easy with some of the other shapes. But this one, the reason I'm liking this one is because it's reminding me of something. It's reminding me of the tape measure or the ruler. So I don't want to go between 0 and 1 when I draw this. I want to go between 1 and 2 because I don't want it to be confusing. So I'm avoiding the 0 end of the ruler. But how is a ruler divided up? If it's a ruler that has inches, it's divided in half with a big line. So if that's 1 inch and that's 2 inches, this is 1.5 inches. It's easy to find. And then it's divided into quarters with lines which are not quite so big. And then it's divided into 8ths with lines that are a little smaller. And there's just something so well organized about this. I think I need to make that longer there. It starts to look more and more like a ruler or a tape measure because it's so convenient the way a standard ruler that measures in inches, it's not a metric system ruler, is divided into things that are cut in half. You divide this into half, then a quarter, then an eighth, and even a 16th. And I can even draw those little 16ths if I want. And then I can use it to measure the length of something, but I want it to be the length of something that is just some weird thing that who knows what it is, like this thing. What is this thing? I don't even know what this thing is. I made it at some point out of construction paper and tape. What is it? I don't know what it is, but what we can do is we can find out how long it is. So we're pretending this is a regular ruler. Obviously, an inch is a lot smaller than this, or maybe I'm a little doll in a dollhouse. That's the thing that happens when you try and draw a ruler really big on a chalkboard, but then it's not the size of a ruler anymore. But I can still figure out how long would that be. Oh, it looks like a nice, clean 3/4. Well, starting from the 1, it's going 3/4 of an inch towards the 2. This would be 3/4 of an inch long. So the great thing about the fraction shape that's done from a rectangle is that it leads us to the tape measure and the ruler, and it leads us something that's really useful that we need to use all the time. And as a carpenter, someone who likes woodworking, I appreciate rulers, and I appreciate the fact that they that you can get rulers in the metric system if you need, but you have rulers that measure with inches because with woodworking, it's all about the inches and the feet. It's not about the metric system. I'm going to take another sip, and then I'm going to start getting into some of the real meat of our lesson, which is I'm going to get back into multiplying fractions. We were doing a lot of that last week, but we're going to do a bit of it this week as well. I need to take a sip of my water first. Remember to take a sip of your water and do a stretch if you need to. Okay, that helped. Next bit of my lesson. Multiplying some fractions. And I want to, this is a review because we did do it last time, but it's important. And when something's important, you should do it a lot. You don't rush through these things in math. It's really good to take your time and do a lot of practice and to see the variety that can happen. And even with things like fractions, a variety can happen. You can have different styles of fraction multiplications, for instance, and that's what I'm going to show. So, the first one I'm going to do is a simple one. I always like to start with simple ones. Give you a quick look. Okay, how about 1/3 times 1/2? Yeah, that's a fairly simple one. Why is it simple? Because the numbers are small. Because the numerators are both ones. It's a good intro to multiplying fractions type of question, which means it's a good one for me to start with in my review. Numerator times numerator gives me new numerator. New numerator, hard to say. Denominator times denominator gives me new denominator. Denominator, not new denominator, not so hard to say. Okay, 1 times 1 equals 1. That was fast. 3 times 2 equals 6. 1/6 is the answer. It worked. We know how to do this. You multiply the tops, you multiply the bottoms. It's tempting to say that, but it's also important to remember the terminology. We multiply the numerators, we multiply the denominators. Multiplication is convenient because it's very straightforward. Another one. How about 3/5 times 5/6? There's Doug's favorite fraction denominator, 6. That's hard to say. Now you just have to slow down. Okay, numerator times numerator. 3 times 5, that's giving me 15. If I know my multiplication tables, this is fairly straightforward. 5 times 6, that's my denominators. When I multiply them, my new denominator is 30. Of course, I can reduce this fraction. And we did talk a little bit about reducing, and we're going to talk about it a little bit today as well. We did talk a little bit about it last week. How am I reducing? I'm going to divide 15/30ths by 1, but I'm going to use a clever form of 1, which is going to be 15 over 15. How did I know to use 15? I wanted to choose the greatest common factor of 15 and 30, and I had a feeling that it would be 15. 15 divided by 15 equals 1. 30 divided by 15 equals 2. And it turns out, oh, our answer was 1/2. How would we have predicted that, looking at this, that the answer would give us 1/2? Well, sometimes we'll predict it, sometimes we won't, but it doesn't really matter if we predict it if we're able to get it, because we know how to do the steps of multiplying fractions, so we get the right answer. Okay, I'm going to erase just this because I'm going to do that one again, but I'm going to do it with canceling this time. How about, well, I don't have to say how about, it's the same question. 3/5 times 5/6 equals, put a bar, get ready to give an answer, nice big bar. Okay, I can cancel a 5 at this bottom with the 5 on that top. In multiplication, you can cancel across two fractions. You can't do two bottoms, you can't do two tops, but you can do a bottom with a top, any bottom with any top, if it's multiplication. When you're dividing, when you're adding, when you're subtracting, no, no, no. Okay, so the 5s can cancel. I'm dividing both 5s by 5, and I'm getting a 1. But I can also cancel a 3. 3 and 6 have a common factor, and I can cancel by dividing this top with that and that bottom both by 3. 3 divided by 3 is 1. 6 divided by 3 is 2. Now I'm multiplying 1 times 1 equals 1, and 1 times 2 equals 2. And what has happened? I have gotten to the same answer. It's correct. Is this easier? Half the students should be saying yes. Is this one easier? The other half should be saying yes, because is either of them easier? It's kind of a matter of opinion, but my answer is no. Neither of them is easier because they both had two steps. This one, the first step was just multiply the tops and the bottoms. The second step was to divide top and bottom by a clever form of 1, taking advantage of my knowledge of how to find the greatest common factors so that I could simplify my answer. This one, I got directly to the answer. So does that mean it's easier? Does it mean I only did one step? No, I did. This was a step that I multiplied when I multiplied the 1 and the 1, but there's also the step of doing the canceling. So it really is a matter of personal preference, I think, which one that you like better. I'm not going to say which one is easier because I think they're both equally easy. They both have 2 steps. Just looking at the chat, making sure everything is okay. And it is. I am going to put up another question, another one with some canceling, but with some bigger numbers in it. I'll erase both of these. And as always, while teachers are erasing and writing, you take advantage of the chance to get that stretch. I think the shoulders especially need a lot of stretching. Is it because they're close to our brain and we're exercising our brain? It might have something to do with that. How about 4/15 times 5/16? Now, I use this as an example for multiplying fractions with canceling because 4 times 5 is, that's easy. 15 times 16, the numbers are getting a little large. The answers are getting a little large. I know you could do it. If you need to multiply 15 by 16, I know you can do it. But it starts being a little slower to do. You have to be a little bit more careful. But the thing with the canceling is it produces smaller numbers to deal with. So that's why canceling is so useful. Okay, how will I cancel this? 15 and 5 have a common factor of 5. I am dividing both the 15 and the 5 by 5, and this gives me a 3 here and a 1 there. 4 and 16 have a common factor of 4. 4 divided by 4 is 1. 16 divided by 4 is 4. Now I can write my answer, and I know it's already reduced. 1 times 1 equals 1. 3 times 4 equals 12. That was fast. Would we have realized that it was 1/12 right away if we had done it the other way, multiplying directly without doing the canceling? Let's try it. 4/15 times 5/16 equals 4 times 5 is 20. 15 times 16. Okay, do I want to run and get my calculator? No, I'm Doug. I like to show that I can do things like that. And I like to talk out loud about how I do them so that people can see, yeah, there is a way of doing this, and it's not the only way. I have my methods, and other people have their methods. If it works, it works. 15 times 16, how am I going to do that? 10 times 15 is 150. 6 times 15 is 90. I happen to know that, but it's not in the 12 by 12 multiplication tables. Even 10 times 15 is not in the 12 by 12 multiplication tables, but 10 times something tends to be easy because it gives you the same something with an extra 0 at the end. 10 times 15 equals 150. 6 times 15 is 90. 150 plus 90 is 240. I can see by looking at this that 240 looks like it's going to be a multiple of 20. And that helps me to realize that the greatest common factor of 20 and 240 is going to be 20. So I'm going to divide top and bottom by a clever form of 1, which is 20 over 20. 20 divided by 20 equals 1. 240 divided by 20 equals 12. I did it. I am reviewing my reducing fractions earlier than I meant to, but it's interesting to compare answering the question 2 different ways and think about how it works, because if you know 2 different ways to do something, it gives you insight into how it works, and that's a good thing. Okay, do I have some more? I have a few more that are a little different, that involve some slightly different looking questions. So let's do them. Okay, I'll erase this. How about when you have a fraction times a whole number? 3/5 times 2. We know what to do, but it's different. It's a little different. In a way, you can say you have an extra step, or you can say it doesn't even count as an extra step because I do it so fast. I can turn 2 into a fraction by putting it over a 1. I can turn any number into a fraction, any whole number into a fraction by putting it over 1. It's useful to do that. I could maybe do this without having to show that. But if you need to show it, you show it. Now it's just a regular multiplication. 3 times 2 equals 6. 5 times 1 equals 5. I can multiply a fraction by a whole number. I knew I could. I knew you could. But I wanted to review that because it's one of those fraction questions that looks a little different. Although it looked different when I first wrote it, and now it doesn't look quite so different. How about 1/4 times 4? Very similar, but this one I'm going to do including some canceling because I have a canceling opportunity. First, I'll show that 4 is equal to 4 over 1. And then, oh, look, a 4 on the top and a 4 on the bottom. I can cancel a 4. 4 divided by 4 is 1. 4 divided by 4 is 1. Look at all these 1s. 1 times 1 is 1. 1 times 1 is 1. I have 1 over 1 as my answer, which means I can just write 1 as my answer. 1 over 1 is 1. Okay. Next one. Okay, I don't know if you can hear that. I can hear something, and it's Mocha barking. And usually that means someone's at the door, but no one was supposed to be arriving today, so I'm going to try to ignore it and hope that I can continue ignoring it because no one else is home. Mocha's the only other one who's home. How about if you have a fraction that has a 0 in it? How about 0 over 5 times 1 over 7? Okay, how am I going to do this? There's a 0. Does it matter? Not really. How do you multiply fractions? You multiply the numerators and you multiply the denominators. Should I let this stop me? I'm not going to let it stop me. 0 times 1 is 0. 5 times 7 is 35. So I have 0 over 35. I have 0 35ths. And what does that mean? It means I have 0. Kind of like that pizza where all the slices were gone. It was equal to a fraction with 0 as a numerator, which means it's equal to 0. There was no pizza left. 0 is my answer. Not to be afraid of. Do another one. 3/4 times 0 over 6. Now, interestingly, I could do some canceling here if I wanted to, but I'm still multiplying by 0. So I have a feeling the same thing is going to happen. Okay. Just taking a look at the chat and taking a look at the time as well. Okay, numerator times numerator. Well, what's different here? Am I just doing the same question again? Not much is different. It's just that the 0 is in the second fraction. Is it going to matter? It's not going to matter. 3 times 0 equals 0. 4 times 6 equals 24. My answer is 0/24. That's also equal to 0. 0 over anything is equal to 0. Not so crazy, but it's good to deal with things that look a little different so that you can figure them out. Now there's someone walking past the window, and I was just checking to see who it is. I hope he doesn't come to the window and start knocking, but now I know who it is, and I know there's nothing to be afraid of, and Mocha's going to bark, and it doesn't matter. So, good. I don't want to interrupt my math lesson. I think I've done all of the multiplications that I had prepared, and that's because that was a review. So now I am going to erase, and I am going to put up the next type of question. And it's division. I'm going to start dividing fractions. Now, we did do a little bit of division last time, but we only touched on it. And this week, we're going to spend a little bit more time on it. In fact, I've put the bulk of my time for this lesson into the division. But we don't want to rush through it. Okay, division of fractions isn't very hard. The students usually start thinking it's quite easy very early in the process. But that doesn't mean that you should do it really fast and rush through it, because that's how problems happen, is when students try to do things too fast. It's why we want to pace these lessons so that there's a lot of chances to practice, a lot of chances to ask questions and to say, what if? Okay, so my first division problem is going to be a very simple basic one because it's the first one. So I'm going to draw 5 squares. And they're not perfect squares because I'm not using a ruler. And what I'm going to say is that these represent 5 rice cereal squares, 5 portions of rice cereal. It's interesting because looking at the size, they look like they get bigger, but I think that's an illusion with the whole chalkboard tilted camera thing. So these are the same size. I'll just make sure you know that. So we're going to take these 5 rice cereal squares and we're going to divide them evenly between 2 people. How do we do that? If you actually had the rice cereal squares, I bet you would already be ready to do it and start working on it right away. But I just want to take my time to talk about this. I can give 2 of them to one of the people, and I can give 2 of them to the other person. And then there's that extra one at the end. What am I going to do? I'm going to split it in half. So I'll draw a dotted line through it. And now we're able to do this. We will give 2 whole squares and a half square to one person, and we will give 2 whole squares and the other half square to another person. So I can do this. And it involves fractions. How am I going to show that? Well, the original problem could be written as 5 rice cereal squares. And we're dividing by 2. So it's like divisions that we've dealt with before we got to our fractions unit. 5 divided by 2. I'm just dividing whole numbers here. That's what this problem really was. But 5 divided by 2 can be written in so many ways. We can write it like this in a line with the divided by sign. But another way we can write it is 5 divided by 2. And I'm reminding you that the division sign kind of looks like a fraction for a reason, because fractions really are divisions. Okay, now the person is knocking on the window. So I hope I don't have to interrupt anything in order to do this. He's walking by now. He doesn't realize I'm here, but he might hear me. Okay. 5 halves is a fraction, and it's also the answer to this question. How do I want to show that? Well, this person is getting 2.5 of these squares. There's 2.5. I can write it like that as a mixed number. And this other person is also getting 2.5 of the squares. And if we add 2.5 to 2.5, we're going to get the 5 squares. We can see that happening. But 2.5 is a mixed number that can also be written as 5 halves. It means the same thing. So how do I want to show this? I want to show it the way I was showing some multiplications. Remember when we had to do a multiplication and we were multiplying by a whole number, but we wanted it to be a fraction. So what did we do? We put the whole number over to 1. So I'm doing that right now with these. 5 can be written as 5 over 1 if I wish. And 2 can be written as 2 over 1 if I wish. Aha. How do we divide fractions? I know you already know because we did do it last week just a bit. How we divide fractions is we turn the second fraction upside down and we multiply instead. Now that I've written this so that these numbers are fractions, I can see myself doing that. I can see what I'm doing. The first fraction stays the same. The division sign turns into a multiplication. The second fraction turns upside down. Now I'm multiplying the tops and I'm multiplying the bottoms. 5 times 1 equals 5. 1 times 2 equals 2. My answer is 5 halves. I am finished. And look, 5 halves. So when we think about this, it's good to slow down and think about one of the more basic problems and think about what's happening and to get that insight. So you have a feeling, yes, it makes sense. Yes, this thing we do where we turn the second fraction upside down and multiply instead, it makes sense. We kind of proved it made sense by doing this example. But I've talked about this example for long enough, so now I want to get into some practice of doing this. Usually your division of fraction problems are not going to look like big pictures of Rice Krispie squares, rice cereal squares. They are going to look like a lot like the multiplication problems we were doing before. Okay, my next one, I have to find it. How about 3/4 divided by 5/6? There, that's my favorite denominator, 6. 3/4 divided by 5/6 is the same as 3/4 times 6/5. Okay. I turned my division into a multiplication. This is why it's deceptive to students to think that dividing fractions is easy. We don't want the student to think it's easy. When you think, all I have to do is turn the second one upside down and multiply instead. Well, once you know that, it does feel easy. But if you think something's easy, you might not practice enough. So I want the students to practice a lot. Okay, now we're doing, it turns into a multiplication. I could even look for a canceling opportunity, but I'm just going to go right ahead and do the multiplication the more straightforward beginner way. Top times top equals new top, bottom times bottom equals new bottom. Numerator 3 times numerator 6 is 18. That's the numerator of my answer. Denominator 4 times denominator 5 is equal to 20. There's the denominator of my answer. I can reduce this. I'm not going to do it right now because I want to focus on the division right now. I can reduce this, but I have done my process. The process works. Let's do another one. How about 2/5 divided by 5/2? Okay, look at it. It's tempting to do canceling, but we don't want to do canceling. This is not a multiplication. Remember, and I've said it before, and I'm going to say it as many times as I have to, with division, addition, subtraction, you cannot cancel across fractions. With multiplication, you can. So if you're tempted to do some canceling with a division problem, don't do it right away. Wait until you have done that step where you write the first fraction the way it is, you multiply instead, you turn the second fraction upside down. Okay, 2 times 2 equals 4. 5 times 5 equals 25. We have our answer. Were we able to cancel? We couldn't judge that here. It was tempting. Look at the 5s, look at the 2s. But I warned you, you can't do that. You have to turn it into a multiplication. At that point, you are allowed to cancel, but it turned out there was no canceling opportunity. It was an illusion when we looked at this version of the problem that we could do some canceling. And turned out we can't do any canceling. We have an answer which therefore cannot be simplified. We cannot reduce it. 4/25 is already to lowest terms. Okay, I'll do another one. I'm going to do some erasing though. And take a look at the chat. And I've seen some questions. I want to look at some of these questions and start answering them. So before I start writing my next examples, I'm going to take a look at that. Students are saying it's easy now and they're happy, and I just like hearing that students are happy because a happy student is a confident student. What is meant by a clever form of 1? This is a phrase that I learned from Aurora. It's a math trick I was always doing. I've been doing it since I learned how to reduce fractions, but I liked Aurora's way of putting it, so I started talking about it that way. When you have, remember we had an answer before that was 18/20. So this is a reducing fractions problem, but that's okay because I was going to do that anyway. When we want to reduce fractions, what we can do is we can divide the fraction by 1. You're always allowed to divide anything by 1 if you want. Anything divided by 1 equals the same anything you started with. We all know this. 10 divided by 1 equals 10. 5 divided by 1 equals 5. 2.5 divided by 1 equals 2.5. Okay, that sounded confusing. I'll get away from that one. 7 divided by 1 equals 7. Anything divided by 1 is allowed because it gives you the same thing you started with. So that means I'm not changing this into a different number if I divide it by 1. But I don't want to divide it by a regular 1. It would just give me 18/20, and that wouldn't change anything. Instead, I'm going to divide it by a clever form of 1, which is when I write any number I want on top of itself. The same thing I was just saying. When you write a number over itself, the answer is going to be 1. 7 divided by 7 is 1. So 7/7 is equal to 1. 8/8 is equal to 1. 10/10 is equal to 1. So I can choose any number I want and write that number over itself, and it really means 1. What number am I going to choose, though? Not just anything. I'm looking at the common factors of 18 and 20. And I'm going to choose one of those factors, ideally the greatest common factor. The greatest common factor of 18 and 20 is 2. So I'm going to divide 18 over 20 by 2 over 2. This is the clever form of 1 that I'm using this time because it's the one that's useful, the clever form of 1 that's useful to me right now. Because 18 divided by 2 works. It gives me a 9. 20 divided by 2 works. It gives me a 10. 9/10 is a fraction that means the same thing as 18/20. It's the same number, really. We didn't change the number because all we did was divide it by 1. That clever form of 1 is very handy when we are reducing fractions. Another question. Why is the second fraction flipped, not the first? The y part is making me feel a little bit like a deer in the headlights. Why? Because I don't question why very often. I'm sure there's a really good answer. But it is important that the student knows that it's going to work if you flip the second fraction and multiply instead. And it's not going to work if you flip the first fraction. So I don't know if that's a very satisfying answer to the question why. When we multiply fractions, we don't have to have the denominators be the same. No, we don't. When we multiply fractions and when we divide fractions, we do not have to have common denominators. We have to have common denominators when we add and subtract fractions. And we are going to get to that. We're even going to talk about it a little bit in today's lesson, the adding and subtracting fractions. But first we learn to multiply. Then we learn how to divide, which is what we're covering right now. We learn adding and subtracting fractions later because they require the common denominator. And that is actually a little bit more challenging. There's a little bit more work to it. You do not have to have common denominators to multiply or divide fractions. Can we multiply more than 2 fractions together at once? The answer to that is yes. But I think Aurora covered that in class on Monday. Oh, and Aurora covered the why question. Why is it the second fraction you turn upside down? She covered that on Monday. Okay, can we multiply more than 2 fractions together at once? Yes, we can. And I'll do it, but I'll do a really quick, easy one because it's kind of a challenger question, and I do want to get back into the division. So over here, I'll do, say, 2/3 times 1/2 times 3/4. I don't want the numbers to be too big. I don't want it to get too crazy. And the multiplication still works. The strategy still works. You multiply the numerators. 2 times 1 times 3. It's just that we're doing more of them. 2 times 1 is 2 times 3 is 6. 3 times 2 is 6 times 4 is 24. We were able to do it. When we had more than 2, we were able to do it. But that's the only one like that I'm going to do. Do you think it's better to reduce than multiply, or multiply then reduce the fractions? Very similar to the question I was talking about before. Is it better to cancel and then multiply, or to multiply then reduce? It really is the same question. And I'm going to stick with the same answer. I do not think either one is better. I think they're both equally good because they both work. And I like it when students know 2 different ways to do something because that really helps people to understand. The person who was knocking at the window before seems to be gone. And I'm glad because he was very distracting. Okay. I have to remember what the last one was that I did. It was that 2/5 divided by 5/2 one, the one that tried to trick us into canceling before we should start canceling. 6/7 divided by 3/7. I like this one. We have a common denominator, but we don't need it. It's a division. But it just so happens that we have a common denominator. So what happens if you just by luck have a common denominator while you're dividing fractions? Well, not very much happens right away because the first thing that we should be worrying about is, well, what's the next step? And the next step is the same next step as all the other divisions of fractions where the denominators were different. Okay, so what do? I do not turn the first fraction upside down. I multiply instead, and I do turn the second fraction upside down. So I'm multiplying. And I can do some canceling now at this point. Oh, look, there's a 7 here and a 7 there. Well, I guess we shouldn't be too surprised, since we had a common denominator in the original question, but dividing fractions requires us to turn one of the fractions upside down, the second one. We end up with a 7 on the top and a 7 on the bottom. At this point, we are allowed canceling. We don't want to try canceling over here. It's not a multiplication, but now it's a multiplication. So we can cancel our 7s if we want. 7 divided by 7 is 1. 7 divided by 7 is 1. And in fact, we can cancel a 3 here. 3 divided by 3 is 1. 6 divided by 3 is 2. And I end up with 2 times 1 equals 2. And 1 times 1, oh, I end up with 2 over 1. I end up with the number over itself. There's that thing again. 2 over 1 is equal to 2. But let's think about this. Is it a surprise that this particular problem gave us a whole number as an answer? When you think about it, it's not that big of a surprise, because if you just look at the numerators, 6 divided by 3 is equal to 2. So 6 apples divided by 3 apples would be equal to 2. 6 oranges divided by 3 oranges would be equal to 2. We're talking about division of whole numbers and fairly simple small numbers that we've done before. So 6 anythings divided by 3 of the same anythings should be equal to 2, shouldn't it? Therefore, 6 sevenths divided by 3 sevenths should be equal to 2. It's tempting to see this as being a big shortcut, but I don't know if I like shortcuts. Shortcuts, when used too often and too early, lead to students who are able to get some questions right, but don't necessarily understand them as well. So I'm not looking at this because I like it as a shortcut. I'm looking at it because it's giving me some insight. The idea that a fraction divided by another fraction when they have the same denominator creates this situation. That's interesting. But when you have 2 with the same denominator, are they always going to give a whole number as an answer? I don't think so. So we have to watch out and not try to jump to too many conclusions about this. So let's try a different one. Not very different. 5/9 divided by 2/9. These have the same denominator. Again, I'm not trying to do any canceling yet because it's not a multiplication, but I am going to rewrite it as 5/9 times 9/2. I'm doing my process because I know my process works and I trust it. Now I can do some canceling though. 9 divided by 9 is equal to 1. 9 divided by 9 is equal to 1, but this time I can't do any more canceling here. And I have 5 times 1 equals 5, and 1 times 2 equals 2. I have 5/2 as my answer. It didn't turn into a whole number. So when you start with a division that has a common denominator, it doesn't have to turn into a whole number. It happened that time because our numerators happened to be, the first one happened to be twice as big as the other one. But 5 isn't exactly twice as big as 2. It's not exactly 3 times as big as 2. 5 divided by 2 gives a decimal. So, or a fraction, if you will. So you have to watch out with looking at patterns and trying to jump to too many conclusions. It's good to look and to think about what's happening, but you want it to make you think and understand. And you don't want to look for shortcuts. I'm going to erase. What is my next one? Oops. Oh, another one that gives some insight. Another one where I see interesting patterns emerging when I look at the question. Just double checking in case there's any more questions, but there were some very good questions there. And asking questions is an important part of learning, isn't it? And this is one of the reasons why we do lots and lots of examples, because when you try to make the examples a little different, it's like asking a question, isn't it? What if I do this? Will it be different? Will it work the same? These are good questions to ask. 5/6, Doug's favorite denominator, divided by 1/2. Okay, it's a division. I'm not trying to do any canceling. I'm going to rewrite the 5/6 and not turn it upside down. I am going to turn the divided by into a multiplication. I am now going to turn the second fraction upside down, and it's 2/1. And I do realize that there's a canceling opportunity here, but I don't always have to use that because, as we have seen, sometimes you can cancel and then not have to simplify later. Other times you don't cancel, but you simplify later. Either way is just as good. So the multiplication, 5 times 2 equals 10, and 6 times 1 equals 6. We have a fraction as our answer. We can reduce this. 10 and 6 have a common factor of 2. So if I want, I can divide them by this clever form of 1, 2 over 2. 10 divided by 2 is 5. 6 divided by 2 is 3. 5/3 is my answer. 5/6 divided by a half is equal to 5/3. 5/6 times 2 over 1 is equal to 5/3. 5/6 times 2 equals 5/3. I'm seeing another pattern emerge. What happened here is my answer has that 5 in it, but the denominator is half as big. 5/6. 5/3. So dividing by a half. What does dividing by a half mean? Dividing by a half means multiplying by 2. And of course we know that because this is what we're doing. We turned a half into 2 over 1, which is equal to 2. So does that always happen? No. Because I happen to have a 1 in my numerator here, and you don't always have a 1 in your numerator in the second fraction. So this time, when I turned it upside down, it turned into that sort of thing, that whole number, which can be expressed as a fraction by putting it over 1. That's only going to happen if you started with a 1 in the numerator in the first place. An interesting pattern to notice. Double checking the time. I think I'm doing quite well on the time. So I want to do some more practice. And I'm going to stop with this looking at patterns all the time. And I'm going to not try to do so much reducing. I'm going to do some divisions. I'm going to do several divisions in a row. And I'm not going to reduce the answers because I'll save the reducing for another discussion. We need more practice with fraction divisions. How many have I done? I've spent a few minutes on it, but I haven't really done that many. If we include our rice cereal squares question, 1, 2, 3, 4, 5. That's not enough. We need lots more practice than that. Let's juggle the numbers, use some different looking numbers. And remember, when you use different numbers, you end up not using so many 1s and 2s and 3s. So you end up with bigger numbers, and you can end up with some fractions that have big numbers in them, which means there's a good chance that you have a reducing opportunity, which I'm not going to do right now. So let's try that. How about, we've used lots of 1, 2, 3, 4. We've used quite a few 5s. I'm going to just keep with numbers bigger than 5 for a while. 6 over 7, why not? Divided by 8 over 9, why not? Let's just use 6, 7, 8, and 9 like this. So you can see that you can basically make up any question you want with any numerators and any denominators. The process still works. 6/7 divided by 8/9 is the same as 6/7 times 9/8. Turn second fraction upside down, multiply instead. I'm not looking for a canceling opportunity either because this isn't a canceling lesson either. It's not a reducing lesson. It's not a canceling lesson. It's a dividing lesson. So let's stick with the dividing for the next few examples. But this puts us in a position where we have to use our multiplication tables quite a bit. No. 6 times 9 equals 54. 7 times 8, 56. Some of the multiplications in the 12 times 12 table that are among the last people learn, actually. And some students are not super confident with the answers to these ones, but that just means you need more practice, doesn't it? So this is a good idea. 54, 56. But I could reduce that, but I'm not going to. It's an answer. It's a perfectly good fraction, 54, 56, even though it's hard to say. Okay, I am going to take a sip of my water, and then I'm going to do another one without erasing, and then I'm going to do a couple more. Okay. And again, why am I looking at this page? I'm now inventing them. And of course, if students type some in, I'll try to use suggestions that students type in. But like I've said many times before, if students become a little too creative and put crazy questions that are just going to confuse the students who are more beginner, I'm going to try to avoid those. Okay, we'll get into a few 2-digit numbers, but we'll try and stay within the 12 times 12 multiplication tables as well. How about 5/11 times 7 12ths. Okay, the bottom multiplication is pushing us to the limit of that 12 times 12 times table. Oops, why am I writing times? Okay, slow down, Doug. You're losing track of what you're doing. We're not going to do 11 times 12. I forgot. This is not a multiplication. This is a division. Okay, so let's put the divided by symbol where it belongs, and let's rewrite our division as a multiplication. 5/11 times 12/7. Didn't end up multiplying 11 by 12 after all. Okay, 5 times 12. That's a nice easy one because it gives a round number answer because involve the 5. 11 times 7. That's fun as well because 11 is kind of fun to multiply by other numbers. That gives 77. Wow, I actually got quite a fraction with quite a big numerator, quite a big denominator, but I can see this is not going to be able to be reduced anyway. I wasn't going to reduce it, but it can't be reduced. 60 and 77 are not going to have a common factor. I really don't think so. Okay, so I'm going to erase and do a couple more. I like this. I'm going to invent some with the numbers a little bigger, just so that we realize we don't have to be scared of dividing fractions when the numbers get a little bigger. So how about now? I keep on looking at this, even though I don't have examples of this. So I'm making them up. I'll start with an improper fraction. How about 11/4 divided by, yes, it's divided by, not multiplication. How about another improper fraction? 9/2. There you go. Okay, so I did dip into some of the easier numbers, but we got 11 and 9 in there. Okay, what first thing we want to do, though, is multiply instead, turn second fraction upside down. We have 2/9 instead of 9/2. We would be able to do one tiny little bit of canceling, but I don't want to do canceling right now. 11 times 2, that's numerator times numerator. That gives me 22. That's good. 4 times 9 gives me 36. Not so bad. We could reduce this answer, but I'm not going to. Another one. How about doing the same one backwards? 9/2 divided by 11/4. Now, the 9/2 is going to stay 9/2, and the 11/4 is going to turn upside down to turn into 4/11 because I am switching my divided by into a multiplication. And now I'm multiplying. 9 times 4 is equal to 36. 2 times 11 is equal to 22. Oh, look. Oh, look. Same numbers, but upside down. Interesting. That's just a pattern, and it's a pattern to see, but it's not very important because what's important is that the process works. Am I going to reduce it? No, not this time. Couple more. Looking at the time, I think there's time for a couple more. And then I'm going to do a couple of reducing fractions, which we've already done several of during this lesson, so I don't have to save as much time for the review of reducing fractions as I intended to. How about, that's just for fun, trying to do something different. A couple of fractions, and I won't even stick with the 12 times 12 multiplication tables, although remember, it's a division. So how about a couple of fractions, very small numerators and very big denominators? How about 1/18 divided by 2/13? It looks like I'm going to have to multiply 18 by 13, but oh yeah, dividing fractions. No, I'm not going to. I'm going to turn the second fraction upside down. It's not going to be as crazy as that, is it? 1/18 stays the same. Divided by turns into multiplication. 2/13 becomes 13/2. I don't have to multiply 18 and 13. 1 times 13 is 13. 18 times 2 is 36. That one's not so bad. And is it a fraction I can reduce? No, actually, I can't reduce that. 13 is a prime number, so its only factors are 1 and itself. So I cannot reduce this because 13 is not a factor of 36. Okay, another one. Improper fractions with really big numerators and small denominators. Same idea, but kind of upside down-ish. How about 15/2 divided by 19/3? That's 15/2 multiplied by 3/19. Same thing happened. look for a second like I'm going to have to deal with a 15 and a 19 or big numbers. Should I run for my calculator? But no, it turns out I'm multiplying the 15 by a 3, which is 45. Not so bad. 2 times 19 is also not so bad. That is 38. 45 and 38 are not going to have a common factor, so I cannot reduce this fraction. Yep, 38's only factors are 1 and 38 and 2 and 19. 2 is not a factor of 45. It's not even. I'm thinking, okay, so that's fun. It is fun. I want to do a couple of reducing fractions examples. I'm looking at my time. Just a couple, but I want to try doing some interesting ones because we have already covered several, and it is a review. So how can I make reducing fractions interesting? By choosing interesting numerators and denominators. So now it's just a single fraction. I'm not doing multiplication. I'm not doing division either. I'm not doing an operation. I'm just reducing a single fraction. How about 28 over 49? What starts being challenging is as you get larger numbers, you don't necessarily look at them and immediately know what the common factor will be of 28 and 49. Maybe you do. The more numbers you become familiar with, the more practice you have, the larger the numbers will be in your numerators and denominators where you will realize what the greatest common factor is. I'm realizing what it is for these, if I'm not wrong. What am I doing though? I'm reducing, which means I am dividing by 1. Remember, we were talking about that before while I was answering a question, which means I am dividing by a clever form of 1. And the clever form of 1 I want to use is 7 over 7. Because I'm remembering that 49 is a multiple of 7, and 28 is a multiple of 7. 7 is a factor of both 28 and 49. 28 divided by 7 is equal to 4. 49 divided by 7 is equal to 7. 4/7 is my answer. That worked. Dividing by 1 works. Dividing by a clever form of 1 works. What if I don't choose the greatest common factor? Yeah, we've seen this before. I'm going to do it. How about 72 over 96? Is this going to work? Yes, it's going to work. Okay, I'm trying to think about what the steps will look like. I'm not sure what the greatest common factor is because the numbers are large. And in order to be sure what factors they have, I would have to start listing the factors of both numbers. But there is another approach, of course, and I could list the factors of both numbers, and it's a great way of doing this. But I also can say, oh, wait, I can see they're both even. If they're both even, they both have 2 as a factor. So I can divide by my clever form of 1, but I'm not going to write the divided by 1 this time. I'm just going to write 2 over 2. 2 over 2 is equal to 1, so I can do this. And it will work because these are both even. 72 divided by 2 is equal to 36. 96 divided by 2 is equal to 48. Be careful with that one. Not necessarily as easy to do in your head. And I have an answer, which is a correct answer. It's a reduced form of the same fraction. But I can reduce it further. The strategy of just choosing something that I know will work without making sure I'm choosing the greatest common factor often will result in it being a multiple step reduction. But I can do the same strategy if I wish. I can divide by 2 over 2 again. Because both of these happen to be even still. 36 divided by 2 is equal to 18. 48 divided by 2 is equal to 24. At this point, they're both even again. I could use 2 again, but I don't want to. At this point, the numbers have gotten small enough so that I can see them and start thinking of what their greatest common factor is instead of just what a common factor is. So I'm going to divide these by 6 over 6 because I know 6 is a factor of 18 and of 24, and I don't think there's any greater common factor of 18 than 24. Am I right? We'll find out when we see the answer, because if the answer cannot be reduced further, it means I must have been right. 18 divided by 6 is equal to 3. 24 divided by 6 is equal to 4. 3/4 is our answer, and it cannot be reduced. When I first wrote it down, I didn't realize it was equivalent to 3/4. The numbers were too big for me to realize that. If I had slowed down and really thought about it and sort of started doing math in my head, I might have been able to realize it. Quickly looking at the time. Oh, and there's some text up here. I am going to answer these questions. I'm going to erase the ones that I did. I like this. I am going to point out one thing, though, which is 2 times 2 times 6 is equal. 2 times 2 is 4. 4 times 6, 24. Now I'm going to erase this top problem. That means if I had listed all of the factors, I should have found out that the greatest common factor of these two numbers was 24, which means I could have divided by a very clever form of 1, 24 divided over 24. 72 divided by 24 is equal to 3. 96 divided by 24 is equal to 4. It could have been done in one step, but it's quite challenging. Now I'm going to look at that question I noticed. That was fun. I always like factors and multiples. It's always been one of my favorite things in math. It was one of those topics when I covered it when I was a student that I was always disappointed when we moved on to another topic. How do you do it if it is not possible to reduce a fraction like 7 over 36? How do you know? How do I know? I think that's what the question means. How do you know if it's not possible to reduce? It's true, this is not possible to reduce. Well, this is where we can slow down and list our factors. 7's factors, 7's prime. Its only factors are 1 in itself, 1 and 7. 36 has quite a few factors. We have 1, we have 36. It's even, so it has 2 as a factor, and I will get 36 by multiplying 2 by 18. 3 works. 36 divided by 3 is equal to 12. 4 works. Uh-oh, I'm running out of space. I didn't leave enough space. Quickly, he goes over here and he erases. And then he does it over again, leaving enough space this time. 36 a little further. 2 times 24 a little further. 3 times 12. 2 times, no, 24. Doug's getting flustered. 2 times 18 is 36. 3 times 12 is 36. 4 times, I put 2 commas, 4 times 9 is 36. And 5 is not going to work, but 6 works. 6 times 6 is 36. So I put a 6 and then I stop because I've gotten to 6 in this direction and in that direction. That's a lot of factors. But is there a greatest common factor? Well, no. 1 is the greatest common factor. 1 is the biggest number that's on both lists, which is how we know we cannot reduce this. That was a bit long. Where do kids have the most trouble with fractions? Well, certainly most students find adding and subtracting more challenging than multiplying and dividing. So adding and subtracting fractions is the most challenging, but you notice how I'm just saying it's the most challenging. I don't want to say about having the most trouble because you have trouble if you don't learn it. But we are learning it and we are going to learn it. And when we take that approach that we're going to make sure that we take our time and pay attention to detail and do a lot of practice, well, what will happen is students spent more time on it, but in the end, they didn't really have more trouble. And remember, you can always send questions directly to us by email. I am Doug@superchargedscience.com. We're nearly out of time. I just wanted to do a tiny little bit, and it's really staying very much on topic of what I was just saying, because the last little bit I wanted to do, I'm getting tangled in my microphone cord. The last little, I know I'm dizzy. Whew. The last little bit that I wanted to do was adding and subtracting fractions, but only when we have common denominators, meaning that the fractions that we're going to work with already have a common denominator. 3/4, no, I don't want to use that. 1/4 plus 2/4. How about that? I can add these because we already have a common denominator. 1/4 plus 2/4. What we'll do is we'll put our equal sign, we'll put our fraction bar for our answer. The answer to an addition of fractions always is the same denominator as the ones you started with. You have to make sure that the fractions you're adding have the same denominator. That's what we mean by common denominator. They already have the common denominator, and the answer will have that denominator as well. But the numerators we add. 1 plus 2 equals 3. So we're able to do this, and it isn't really a lot of trouble, but we're starting off with the nice easy one, which is what we always want to do. Start off with the nice, easy, simple ones. 3/7 plus 1/7. The denominator is already common. The answer will have that denominator as well. 3 plus 1 equals 4. The rules are different than multiplication and division of fraction rules. You have to learn the rules that go with addition and subtraction. We need a common denominator, but we have one, so we can proceed. 3/7 plus 1/7 equals 4/7. Subtraction. I may as well mention subtraction because you know what? It's different, but no, it's not. It's really the same logic. I can do subtraction of fractions very quickly if I start with fractions that have a common denominator. So 5/6 minus 1/6, Doug's favorite denominator. I can do this because my answer has to have the common denominator that I had to have in the two fractions I'm subtracting. But since they both started as being fractions over 6, it's okay. I can do it. The answer will also be over 6. 5 minus 1, that's the only difference. I'm not adding. I was adding here because there's a plus, but this is a minus. So I'm subtracting 5 minus 1 equals 4. 4/6, which can be reduced, but we won't worry about that right now. When you add fractions, if the denominator is common, you can go ahead and do it, but you are not adding the denominators. Your answer has the same denominator. The numerators you add. When you're subtracting fractions, you can go ahead and do it if the fractions you're subtracting have the same denominator. The answer will also have the same denominator. Adding and subtracting fractions have a lot in common with each other. One more example, because I'm nearly out of time. I am out of time. So I'll put 5/9 minus 2/9. Denominators are common. The answer will have that denominator. 5 minus 2 equals 3. 3/9, which can be reduced, but we won't worry about that right now. If the denominators are common, we can subtract, we can add, and we'll move on next time to doing some where we don't start with common denominators, and we'll learn how we deal with that. Just like everything else, there's a process that we have to learn, and we have to practice it a lot. So with that, I will say thank you very much for being here. As usual, it has been a pleasure. Goodbye from me. Goodbye from my beautiful assistant Mocha, and goodbye from that guy who was knocking on the window before. I can't wait until next week where we can do it again. And I will just wave.